Sorry about the delay. Okay, so this is work with my former student, Mohammad Hosseini, and Shervin Shirmohammadi. And Shervin and I were the supervisor. Lucky student had 2 supervisors. So Mohammad has graduated. This is work from his master's thesis that he did at Simon Fraser University, and he is now at University of Illinois Urbana-Champaign. The motivation for this work was that we're interested in energy conservation on mobile devices. And as we all know, the technology is advancing faster than battery technology, so the problems are getting more and more severe. And 3D games are becoming more popular. They're even hungrier for power. And the textures, 3D textures, are very bulky, demand a lot of energy. And in fact, the wireless circuits on these devices are consuming a significant fraction of the energy, usually at least a third. When you're playing a game, you can't turn off the screen. So if you want to save energy, one place to focus is on the wireless circuits. So our goals were to increase the battery life by reducing the amount of energy for the radio circuits to stream 3D textures. And we want to maximize the quality of these textures within an energy budget. So, and also we had a minimum quality that was acceptable. So there were 2 constraints. So it's a constrained optimization problem. And we approached this problem by assigning importance values to textures. So the game designer will do this, and so the avatar in the game is going to be higher priority than the grass in the sky. So you assign this, and when you have to make decisions, you're going to use the importance values as part of the criteria. The user specifies a quality constraint. This is the maximum compression the user will accept. We used a very simple measure of quality. It's just the importance value times the size. Figuring that if you have more pixels, then it's going to be higher quality. The value also affects it. So it's a simple model of quality. The user sends an energy budget to the server. The server uses a linear model of energy consumption to estimate how many bytes it can download with that energy. And the linear model is a pretty good model of energy consumption. Well, it's a fairly naive model, but we did some measurements and it was relatively linear. And so then the server uses the download budget, the importance values, the quality constraint, and also we're going to use user feedback about the actual energy consumption to guide decisions about how to adaptively compress the textures as you're downloading. So this is a follow-up study. Our first study I presented last year at MMSys in Oslo. And it was just, it was a simple, it's not a real game. It's just, looks like a game, it's not a real game. There were about 100 textures. It doesn't look 3D, I can't really show 3D on the screen. This is a screenshot. We used the same textures in this follow-up study. And the way we did compression was very simple also. It's just downsampling. And so the textures were powers of 2, and we just downsample by replacing 2 to the I by 2 to the I blocks. So this is showing a texture overlaid on a pillar that was invisible in the previous scene. And the one on the left is 512 by 512, which is our highest resolution. And then each one going to the right is a factor of 4 grainier. So it's visible. And the results of that were that we did see that there were improvements in quality when we were using simple reading heuristics to decide what to compress and not to compress, and by how much to compress, or how much to downsample. And we concluded that this was a promising way to improve quality within a fixed energy budget. But it was a pretty simple study. And some of the limitations that we tried to address in this follow-up study were that it was a single static scene. So everything's known in advance. You stream it all at the beginning of the game, and then that's it. So the algorithms were offline. They didn't adapt to dynamic conditions. And the energy model didn't include actual energy consumed. It was just an estimate. And also, we didn't really have an optimal solution to benchmark it. So we addressed all these things in our follow-up study, or at least to some extent. So we allow dynamic scenes here. So objects arrive with their textures and they leave. And the arrival and departure times are not known in advance, so we have to react to them in real, online. The energy is only known approximately, so we're going to use user feedback to adjust as we go. And we have a benchmark algorithm that's optimal, very close to it. And the main contributions here are two algorithms that adapt to dynamic conditions. The first one adapts to differences between the energy that we predicted with our linear model and how much was actually used. The second one also adapts to arrivals and departures online. And we achieved an improvement in quality within these constraints. So the problem statement is to stream all the textures within the download budget and a quality constraint specified by the user, and maximize the average quality over the duration of the game, which will save time to you. And in the process, we're going to have to adapt to differences between estimated and actual energy, and we're going to have to adapt to the arrival and departure of objects and textures. So a little bit of gore here, I'm afraid, but it's not too bad. So there's a set of full resolution textures. Each has a size before you scale it. The value that's assigned by the game designer, and our simple model quality here is just the value times its size. And the idea here is that if you downsample a texture, you're going to reduce the quality. It's less resolution. And we have an arrival time and a departure time. So that's the time that it's visible. This is really making a lot of noise. This is the time it's visible in the scene. The length of the game, the download budget, our maximum compression is going to be of this form. In our study, C was 4. So we're going down by powers of 4. And this is the maximum you're allowed to downsample and still have the quality be acceptable to the user. What the algorithm actually streams is a set of textures that each of which corresponds to one of the original textures, but now it's going to have a scaled size. So the size of this one that we actually stream is the original size divided by whatever the compression factor was. The value is the same. The quality now is going to be the scaled size times the value instead of the original. And the arrival and departure times are the same as the original. So, and now I can formally state the problem. Okay, so we want to stream all textures within the download budget and the quality constraint Rmax, and maximize the average over the game time. So this is maximizing the quality, summing over all textures that are streamed, of the quality times the time that they were actually visible. And we can expand this. It's the value factor divided by the original size scaled down by this. So we maximize that subject to this constraint that the sum of the sizes of these textures doesn't exceed the download budget. And the compression in each texture is no more than the maximums that the user will allow. So I'm going to try and not have too much more mathematics. There's a little bit. This one has the most. This is our benchmark algorithm. So this is a near optimal algorithm. It's an NP-hard problem. It's a multiple choice knapsack problem. It's NP-hard, so we're not going to get an optimal solution. We can get very close using a greedy algorithm. So this is the contribution of this texture to the average quality if we don't do any scaling. So it's just its value times its size times the time that it was visible. And what we do here to account for deviations in the actual energy used is we're going to modify it. So I won't get into too much detail here. This is a range of deviations. So the actual amount of energy you use is going to be 1 plus or minus some percentage within a range. Delta controls the range. We try different ranges. So this was to try to account for these differences in estimated and actual use. This is, if you scale all the textures by the maximum allowable, this is the minimum amount of the budget you need to stream them. So whatever is left of the download budget is what you have available to improve quality. So that's what we're working with. You have to at least stream them all at minimum quality. So we sort them by this ratio from largest to smallest and just allocate download budget to them in that order. It's a standard greedy heuristic, which basically gives you the most quality per unit of size. And this got us within a couple of percent of optimal. We can estimate the error bound quite accurately. So this is our benchmark, and then we had two algorithms that we compared to it. The first was, we call it semi-online. And here, this algorithm knows everything, almost everything the benchmark algorithm knows, except for the energy variations, which it has to react to online. So to test this out, the idea was to study the effects of the deviations on the quality. So we apply the algorithm with no energy deviations. We just apply the benchmark algorithm. And that gives us some scaling factors for the textures. We sort the textures by actual arrival time, and then we compute these target values. This is the amount of download budget we should be using if there were no variations. So this is what the optimal algorithm would do if the energy was exactly what you expected it to be. So these are the targets, and then we start streaming them. We stream the first one. The user sends back and says, here's how much energy you used. And then we compare that to what we were supposed to use, and and we adjust the next one according to whether we were above or below the target. And we just keep doing this. This is the first, we call it semi-online. And then the online algorithm doesn't really know very much. It knows the textures that it has to stream, and knows their values because the game designer assigned it, and knows the game time and the download budget and the constraint. It doesn't know when they're going to arrive or depart, and it doesn't know anything about energy deviations. So we're trying to figure out what the effects of the arrival and departure times are on the performance. So we can't even calculate this thing now, because we don't know the departure and arrival times. There's not very much we can do. What we can say is that we have a download budget D, a time T, so we should be using about this much energy per unit of time. So what we do is the first texture arrives. So you compare the download budget that you have, or texture I arrives, you compare the download budget you've used so far to the target. So after T time units, you should have used this much energy. And if you're above or below, you adjust the following ones. So this is online in the sense that it's reacting to these dynamic events. So these are the algorithms. I'm not going to talk too much. This is too much detail. We did a bunch of test sequences, permutations. We tried 5, 10, 15% plus or minus energy deviations. These were all randomly generated in these intervals. 0 means no deviations. The download budgets were, this is the total size of all the textures. So if you had that much download budget, you wouldn't have to do any compression at all. So we looked at 5, 10, 20, and so on % of the download budgets. We tried 2 different quality constraints, and we ran 10 experiments, averaged them, and so on. And we did this for all the algorithms. So this is what the total quality looked like. And this is a small sample of them. So this one here, this is with no energy deviations, and this one is with plus or minus 10% range for energy. The online algorithm is this one. It has the worst performance as we would expect. The red one is the semi-online. The benchmark algorithm is the blue one. This is the optimal value. And this is just showing 2 different compressions. This is 64 and 16. 64, you have a lot more choices. You're allowed to compress them quite a bit more. So this benefits the algorithms. They have more to work with. They have more choices. Over here, since the energy deviations are 0, the semi-online and the benchmark are the same algorithm. There's no difference. So the things we observe from this is that the quality, of course, increases with the budget, because you have qualities based on size. You have more budget. The performance differences also increased with the budget. So what happened was the gaps between these algorithms increased as you get more budget, because the algorithms that have more knowledge to work with, the offline and the semi-online, can make better choices. So the more budget you have, the more that benefits you. We calculated competitive ratios. This is a standard way of measuring online algorithms. You compare it against an offline. So it's this ratio. This was for the semi-online and the online. The competitive ratio for the semi-online was quite high. It's around 90%. For the online algorithm, it's a bit lower. It's a little bit under 80%. Still not bad, considering how little it knows. And the higher end of the range was for where Rmax is 64. This is because you're allowed to compress. You have a broader range of choices. And so the algorithms that are adapting have more choices of how they adapt. The differences between the semi-online and online are bigger than between the offline and the semi-online. And what this told us was that the knowledge of arrivals and departures is more valuable than knowledge of energy deviations. So you can take more advantage of it. The last thing here is actually on the next slide. We broke it down by, we had 3 classes for the 3 classifications for the textures. So we broke it down to see what happened there. And the gaps among the algorithms increased with the class. So what we see here is this is one sample here. This is max compression 16 and inner deviations plus or minus 10%. So these are the class 1. These are the least important textures. These are the middle ones, and these are the most important. And we can see what's happening is that, and this is the sum of the 3. So what we can see is that as the importance of the textures increases, the offline algorithm takes more advantage of it. And so the gap here is bigger than it is here. And in fact, for this least important ones, the online algorithm outperforms the optimal algorithm because it's making bad choices. It's putting too much its download budget into the least important textures. So this tells us that the classification of textures also is something you can use effectively. So the conclusions from this were that you can achieve good quality within these constraints, and that adaptive algorithms can improve the energy consumption in a dynamic game setting, and that they can adapt to these energy deviations. We have some future work planned. We, of course, like to study more sophisticated compression methods. This is really simple. And we'd like to measure quality properly, either quantitatively or with user studies. I just have to find some users. It's not a very interesting game.
Not by this one.
Any volunteers? Also, I want to measure the actual energy consumption using an experimental test bed. And this is the test bed. And we've actually built this thing already. This is an HTC EVO 3D smartphone. So it's a 3D, a stereoscopic screen, and this is the back here. There's a stereoscopic camera. You don't need glasses, it's 3D just watching it. I had a heck of a time buying it. Best Buy didn't want to sell it to me. Nobody wanted to sell it to me because I didn't want to buy a phone plan. And they couldn't figure out why would you buy a phone and not a phone plan? I said, I'm not going to make phone calls with it. And they thought I was crazy and wouldn't sell me the phone. So it took me about a month to buy this thing, $600. So the first thing that we did was we took it apart and replaced the software, and we took, this is the battery. We used a 3D printer, and we made a cradle for the battery, and you can't see it, but we made a plug the same size as the battery, stuck it in the back, and wired them together. And so the wires, so now the battery is here and the phone is here, but they're connected through these wires. And this board here is sampling the voltage and current once per millisecond, doing an analog digital conversion and sending it through a USB port to our PC, which is running software, and we can monitor the energy on in real time, the voltage and current in real time, and also store it for later analysis. So we haven't actually done the experiments on this thing, but the test bed is already in functional, just waiting for another grad student. So I think I'm actually on time here.
Any questions?
I have a question about the value. So you add the value to give the developer an indication on how important one of the textures is, right?
Mm-hmm.
And it's multiplicative. It cannot override a short time during which it's important, right?
Yes.
I wonder if that is dangerous for an actual game, because you may have a texture that actually shows something important.
I think you're right, and also as textures move from the background to the foreground, they're going to change importance.
Right.
And if they're on the side, they're maybe not as important as if they're in the center. So probably we should be doing something more dynamic about that. But I think you could tag the textures, but probably you should be adjusting them as well. We didn't look at that, but that's a good suggestion.
I suppose you really need user tests, right? On what is it? Is it, do I need the power of something? Do I need a delta that just replaces the scale? It's super important.
Yeah.
I have no idea.
I don't know. Yeah, we'd have to do user tests.
Okay, so is the cache also included in the optimization? So do you also control which texture is loaded into the cache?
Oh, that's a really neat question. When I formulated this thing, I actually did the whole thing with the cache in it. And so then you have a memory management problem on top of this. And I did this when I was on sabbatical, and I was visiting a team that does scheduling problems. And I formulated this thing from it, and it was just the problem from hell. It was so complicated, we couldn't solve it. But maybe we could do it experimentally. Theoretically, it was just, we could do parts of it, but it's a very hard problem. Thank you.
We'll take those three.
Okay,
Restaurant.
So my question may be more a meta question, but do you know any games that already use streaming? Because all the mobile games almost, I know they all download all the textures to your device, and then there's no connection needed anyway.
right.
So what are the other applications that use such a way right now?
Well, I don't know any commercial games that do this, but our idea was that if you do have a limited cache, it was part of the motivation. And textures are appearing and disappearing as you change your view, you're going to have to restream them. This is what made the scheduling problem really hard. But we thought this was a realistic scenario as games get more complex. But I don't know a commercial game that does this.
So I was just wondering, do you have an idea of the expected savings in battery life, or I mean, is your battery going to last twice as long?
Yeah, I think we have to do this.
I think you might have to show up next year.
Yeah. This is phase 3. I hope I'm going to have this done by next year.
I'm not plugging the conference or anything. Throwing that out there.
Why would you?
A subtle question. You assume your compression factors 4. So you said from sampling, we sample go down to by 2, that's compression factor 4. That's true when you assume uncompressed textures being streamed over, but most textures are always compressed into better formats, which means when you subsample, it doesn't necessarily compress to 4 factors, it goes go down to 20% only, right?
It's true.
So that would mean your formulas would make your C's not uniformly 4, it would make it C per texture, variable number.
Yeah.
So it would make your formulas more ugly than they were. So
It would. I mean, that was more for the theoretical problem, because I think as long you probably use mid-maps or something anyway, and you would have maybe a database of different resolutions, and you have to choose one. So they wouldn't necessarily be by 4. So we were kind of visualizing you might store different resolutions, or possibly layers, enhancement layers.
So another one with the importance of textures, you say you assign a number, but maybe I have 10 grass textures for nice variety, but I would prefer to have one high-res grass texture repeating rather than having 10 low-res grass textures. So is there a way to kind of merge these into, instead of assigning an importance to a single texture, assigning importance to a group of textures, so that I could start cutting down on variety rather than quality?
Well, you would be cutting down on the size. You'd
So
be
if I'm
reducing your choices of how many different sizes as well, wouldn't you?
If I have 10 different types of grass which I tile over, okay, that's 10 different textures, so you're assigning importance to 10 different textures, right?
Well, I see.
I'm saying these are not 10 different textures, they're actually one different texture.
One texture repeated 10 times.
Yeah, yeah. So I could assign an
Oh,
importance.
they're slightly different.
Yeah.
But they're essentially the same, right?
Yeah.
So you could substitute.
Yes, you can
Or
substitute. And in fact, the game that I flashed by you very quickly had 3 pillars in it, and they all had the same texture overlaid on them. So we only streamed that texture once, in fact.
No, I'm saying in real games, because they have a variety of the same texture, they kind of want to do that, so you can just bring it down to, as you said,
Yes.
have a higher quality version of one texture,
True. Yes.
cut down on variety rather than cut down on quality.
Yes. Yes. For sure. That's a good idea.
And since I'm session chair, I get to ask one last question.
I'm nervous.
You know. So, just following up on this question. So, the texture, I guess I have 2 parts. So, are you thinking about using like PSNR or something? Because you know where they are? And the reason I ask that is that it seems like because you're talking about texture compression, right? Really, it's the stuff that's in the texture that's important. So if you've got large, very fine detail, that gets washed out pretty quickly,
Yes.
as opposed to larger.
Yes.
And so it seems like if you just went with an objective measure, PSNR.
Well, that's what I meant when I said we were going to measure the quality properly. I had PSNR in mind, but I also think we need to do some user studies to be realistic. I think we need to do both. But PSNR is the one I would use.
Okay, that wraps up